Welcome back to AP Calculus BC. We're still in the midst of our second topic, which is called series convergence tests. That's kind of a weird topic because we haven't defined series yet. We don't know why it matters if they converge, and we haven't learned any tests for them yet. However, we've really been building that foundation for series by discussing sequences first. We'll talk about how sequences are linked to series down the road. And today we're going to study one really special type of sequence, which is known as a geometric sequence. We actually briefly talked about a geometric sequence in the past, and I think I even filled you in on the difference between an arithmetic mean and a geometric mean. But go ahead and refresh your memory about what that is. I'm actually not going to go back through it again. We did that on a previous video, but there's space here so you can write that down. Hopefully you've gone through and refreshed yourselves on what a geometric versus an arithmetic mean is. Really, it's kind of more of a fun reasoning behind the names than anything we're going to use too much today. So let's get to it. Geometric sequences have a lot of important uses. We will see what some of those uses are later, not today, but later on. And they're generally written in either the form a times r to the 0th, a times r to the first, a times r squared, so on and so forth. Or they sometimes will leave off the r and write it as a times r, and so on and so forth. A is oftentimes known as the scale factor, and we've discussed this in the past. R is, of course, the common ratio. We're going to rewrite each sequence below so that they fit this general form up here of a geometric sequence, and then we're going to identify the scale factor and the common ratio. Let's take a look. Our first one, we're going to rewrite this so that it fits a times r to the 0th, and I think maybe the easiest way to do that is probably just to figure out what the common ratio is first. So as a reminder for that common ratio that I'll abbreviate with CR here, it's lowercase r is pretty common, you take any two consecutive terms and you do 8 divided by 4, and you get 2. 16 divided by 8, 2. 2 divided by 1, 2. Common ratio is definitely 2. So we're multiplying by 2 every time. So then a, one of the easiest ways to determine a, is just use the first value here. Okay, so I think a is going to be 1, and then we're multiplying by the common ratio to the 0th power. Okay, next up, a is still 1, but now we have the common ratio to the first power, and we can continue on through. We get the common ratio to the second power. Common ratio to the third power is going to be 8, I think, and the common ratio to the fourth power will be, of course, 16. One more of these times 2 to the fourth, and then go from here. So that means that my scale factor is 1, my common ratio is 2, and we get the idea. Go ahead and pause and try these other 3 problems, and then you can come back to me and make sure you did it all right. Okay, hopefully you've now unpaused and we can take a look at the second one. For our second one here, we are going to do the same thing. You'll notice that we're multiplying by 2 every time. I think we can probably rewrite this as 3 times 2 to the 0th, 3 times 2 to the first, 3 times 2 squared, and so on and so forth, which tells me that we scaled by 3, a common ratio which is 2. 2 more of these. My common ratio here I think is going to be a negative number. I think we're multiplying by -3 each time. That's why we bounce or oscillate back and forth. And I think if we rewrote this, it'd be 1 times 3 to the 0th, 1 times 3 to the first, 1 times 3 to the second, and so on and so forth, except it's -3, isn't it? So that was silly. We probably need to throw some parentheses on here. If you don't throw on parentheses, you're not quite right. And then we should be good. Last one. It looks like I think we're dividing by 2, but with a common ratio we usually do multiplication, so I'd say we're multiplying by 1/2 each time. And I'll give you 2 different ways to write this if you would rather do it with division. But I'd say the more common way would be 28 times 1/2 to the 0th, 28 times 1/2 to the first, 28 times 1/2 to the second, and so on and so forth. However, if you really enjoyed division, you could say 28 divided by 2 to the 0th, 28 divided by 2 to the 1st, 28 divided by 2 squared, and that's fine as well. As mentioned before, one of the fascinating facets of geometric sequences is that any 3 consecutive terms can make up the geometric mean. So if you have your first term, second term, and third term, then we say a sub n plus 1 is the geometric mean of both of those, right? You add them together, or I'm sorry, you multiply them together and then take the square root, and you'll get the value in the middle. Now, we want to look at geometric sequences and see what causes them to converge or diverge. I think that's what we covered last class. So what you will need to do is use your calculator, graph each of these in sequence mode, and determine, do these sequences converge or diverge? Okay? And then once you've done that, we can come back here and we'll see how you did. Well, if you did things correctly, I think you should see that this first one should converge, right? It actually sits above the x-axis and drops down. The second one is also going to converge, though this one is that cool oscillating one where it kind of starts high, then gets a little lower, and then it just bounces back and forth. And the last two are both going to diverge. This first one, because you're multiplying by a number bigger than 1, will increase without bound. And this last one will start small, but then will start to increase larger and larger and larger, and eventually increase without bound. So when does a geometric sequence converge or diverge? Well, I think what's going to happen here is it all depends on r, what you're multiplying by, right? So if we think of that generic form of a geometric sequence, a times r to the nth power, then we have 3 possibilities. Either r is going to be less than -1, and we saw that up here. R was less than -1, and if that happens, then the sequence oscillates without bound, meaning it gets bigger and bigger and bigger, which means the sequence diverges. And it does ask you to draw a general graph of what's happening here. So if r is less than -1, then you are going to get a sequence that starts small, maybe like here, and then the next term will be negative and it'll be here, and then the next one will be a little bit bigger, then a little bit bigger, and then a little bit bigger, and so on and so forth. And if you wanted, you could do a little, like, some little lines so you can kind of see that it's actually connected like this. Sometimes it's tough to tell. But yeah, that's going to diverge. However, if you take the absolute value of your ratio, and that answer is between 0 and 1, then our sequence converges. Now, it's actually a little redundant to put this 0 right here. A lot of times people will just write that as the absolute value of r is less than or equal to 1. Let's make sure that it works, or we can apply it up above. If you take the absolute value of r, is that between 0 and 1? Yes, it converges. Is this between 0 and 1 when we do the absolute value? Yes, it converges. Are either of these between 0 and 1 when you do the absolute value? No, they're both greater than 1. And so if we wanted to graph this, you're really going to get 2 different possibilities for graphs here. Really 3, I guess. Either your graph is going to approach the x-axis like so. It could also be below the x-axis if you wanted. Or if your r was negative, that's where it's going to do something like this, and it's going to oscillate to the x-axis. Last but not least, if r is greater than 1, the sequence will diverge. And we know it won't converge to a number because when r is greater than 1, that's just going to make your sequence grow without bound. But we only talked about r, so what does a do to our sequence? And it turns out that a does nothing, right? So how does a affect your sequence? It scales your sequence up or down. So if a is a large number, it's going to make your values of your sequence larger initially. If it's a small number, it makes it smaller, but it does not affect convergence. A does have its uses down the road, but nothing for here. So this is actually a very quick lesson. Let's go ahead and finish this off, and then you guys can do some practice problems. We have a couple things to do here. We're going to start by rewriting the sequence so it fits that geometric standard form, that a times r to the nth power. And then we're going to identify if the sequence converges or diverges, whether the sequence is monotonic or if it oscillates. And then lastly, we're going to list the first three terms of the sequence. Okay, so looking at this sequence, I think we have 1 times negative 0.3 to the nth power. Okay, or it might even be nice to rewrite this as 1 times negative 3/10 to the nth power, right? We know it's negative 3/10 because we read this as 3/10, and so you write it as 3 over 10. All right, let's start with A. Identify if the sequence converges or diverges. Well, if I do the absolute value of r, the absolute value of negative 3/10 is 3/10, and 3/10 is certainly less than or equal to 1. Therefore, this sequence converges. Imagine multiplying by 3/10 over and over again. It's going to make your output smaller and smaller and smaller. This will actually converge to 0 if you wanted to be specific about it. So this was part A. Part B. Is our sequence monotonic or does it oscillate? Well, monotonic means is my sequence either getting bigger or smaller, right? Increasing or decreasing. Or oscillate, is it bouncing back and forth between values? Well, since we're multiplying by a negative number here, I think we're going to be oscillating, yeah? Right? If we bounce back and forth, we could even write it like this. R is less than 0, which means we are going to oscillate, because every time you multiply by a negative, it flips the sign back and forth and back and forth. And lastly, list the first three terms. Well, we're just going to have to multiply, and notice our first term is just going to be negative 3/10. That's easy. Okay. Then we multiply by negative 3/10. That's 9 1/100ths. Negative 27 1,000ths. And then it goes from there. Easy enough. Let's do one more. E to the n plus 2 times pi to the negative n. That doesn't even seem like a geometric series. Well, let's try to deal with this a little bit. I think we can probably rewrite this as e to the n plus 2 divided by pi to the n, because we can use that negative exponent to send pi to the denominator. And then we can go a little bit further. We could say that this is e to the n times e squared divided by pi to the n. Right? We can split exponents that are adding. And we can even go a step further. I could rewrite this as e squared times e to the n over pi to the n. And even one step further, don't forget that if you have multiplication or division all to a single power, you can factor that power out. And look, I think we have a geometric series. We have a that's hanging out front, and then we have our ratio in between. Let's go through our three steps. First step, does this series converge? Well, e over n. So we have the absolute value of r, which is going to be the absolute value of e divided by n, which is just e divided by n. However, e is 2.718 something something, and I wrote n here multiple times. I think that's because I was saying n. This should be pi, sorry, and this should be pi, and this up here should be pi. Whoopsies. And pi is 3.141, so on and so forth. Decimals don't really matter in this case. This is approximately 2/3, and 2/3 is certainly less than 1. Therefore, this sequence certainly converges. Part B, is this going to oscillate? Are the signs going to bounce back and forth? Well, I don't think so. I think our radius e over pi is definitely greater than 0, which means our sequence is going to be monotonic. That means when we multiply by e over pi over and over again, our values are just going to stay positive and decrease because we're multiplying by approximately 2/3, which means they get smaller every time. Last but not least, the first three terms. Well, my first term, when I substitute in 1, we're going to get e squared times e over pi. I think it's going to be e cubed over pi. When I substitute in 2, we get e squared times e squared. That's e to the 4th over pi. And when I substitute in 3, I think we get e to the 5th over pi. So that's really all we had to do today, play around with those infinite sequences, specifically geometric sequences, be able to work those couple things. As always, I have our answers posted on Teams if you need any help. Hopefully this is a pretty mellow day, and I'm excited to get to our next lesson.